Hello, my name is Katina Russell, and I'll be talking about efficient construction of directed hopsets and parallel approximate shortest paths. This is joint work with Nyren Kao and Jeremy Feynman. The single source shortest path problem for directed graphs is given a directed graph with non-negative edge weights to return the shortest path distance from a source node S to all other nodes in the graph. Dijkstra's algorithm solves shortest paths in m plus n log n time, where m is the number of edges and n is the number of nodes. However, Dijkstra's algorithm is not a parallel algorithm, and our goal is to find a parallel algorithm for this problem. Low-work parallel shortest paths algorithms depend highly on the longest chain, which is the number of hops on the shortest path. So from S to V, the number of hops is 3, and from S to T, the number of hops would be 5. Based on this observation, one idea for parallel shortest paths is to shorten the number of hops on the shortest paths. So we add shortcuts, which are weighted edges, to the graph to reduce the number of hops on the shortest path. Here we've added the edge from S to V with weight 3. Now the path from S to V is just 1 hop and the distance is still 3. A hopset is going to be a collection of shortcuts. We want a good hopset with quality features that I'll show next. Now I'll get into the definition of hopsets. So for a weighted directed graph, a hopset is a set of weighted edges such that for each pair of nodes uv, there exists a path p that goes from u to v that contains at most h hops, and the distance of p is at most a 1 plus epsilon approximation of the distance from u to v in the original graph, and no shorter than the distance from u to v in the original graph. And so h is considered the hop bound, and the size of the hopset is the number of edges that are added. So in this example, the hop bound is 3 because you can get from one node to any other node in at most 3 hops. And the size of the hopset is 2 because we've added 2 edges. Now I'll show an example of an inexact hopset. So here we have an unweighted graph, and the path from the node H, which is on the bottom left, to the node L, which is on the right, is 4 hops. So now we add shortcuts, which are shown in red, and the weight of each shortcut is shown next to the edge. And so now the path from H to L is 3 hops by going from H to I to A to L, but the distance is 5. So now we have a distance that's a 1.25 approximation of the distance in the original graph. So in this example, the hop bound is 3 because we can get from one node to any other node in the graph in at most 3 hops, and the hopset size is 4 because we've added 4 edges, and epsilon is 0.25. And so in this example, the distance from H to L is a 1.25 approximation, but the rest of the shortest path distances are exact. Now I'll go back to explaining our title: efficient construction of directed hopsets and parallel approximate shortest paths. So by efficient, I mean the algorithm can construct a hopset in nearly linear time, where nearly linear means O tilde of m, which is m times some polylogarithmic factor. And once we have a parallel algorithm for constructing a hopset, we can use that to solve parallel approximate shortest paths. Using hopsets to solve parallel approximate shortest paths is not new, and that was done by Subramanian and Klein in 1997. In this talk, I'll be just showing the sequential unweighted version for constructing a hopset. Now I'll go over some previous results for hopsets. For directed graphs, there exists an exact hopset due to Ullman and Yannikakis and Subramanian and Klein. They have linear size and root n hop bound, however the runtime is high, being m times root n. Our hopset is approximate, has nearly linear size, n to 1/2 plus little o of 1, hop bound, and has nearly linear runtime. For undirected graphs, a lot more progress has been made. Cohen gets a good hop bound, but the work is polynomially more than we want. Miller, Peng, Vladu, and Siu get linear work and a polynomial hop bound. Elkin and Neiman have a couple of papers that improve the trade-off. They're able to get a linear size hopset with subpolynomial hop bound. However, the approaches that are used for the undirected graphs don't work on the directed graphs. For parallel approximate shortest paths on undirected graphs, There's also some results that don't use Hopsets. These are due to Lee 2020 and Doney, Stein, and Zong 2020, but again, these approaches do not work on directed graphs. Now I'll go into the algorithm. Our goal is going to be to efficiently build a Hopset, meaning it has nearly linear runtime, nearly linear number of edges, n to the 1/2 plus little of 1 of hop bound, and a 1 plus epsilon approximation. In this talk, I'll just be showing the unweighted version, and the algorithm is based on algorithms for reachability by Feynman in 2018 and Jumbalapati, Liu, and Sidford in 2019. For them, their problem is to add a set of shortcuts to a directed graph such that the diameter of the graph is reduced to n to the alpha for some alpha less than 1. Our algorithm is going to be trying to build a Hopset, so we're going to be more concerned about the distance. So our algorithm is going to be parameterized by a distance guess d, and we're going to run the algorithm for a particular distance guess d, and then repeat the whole algorithm for all possible guesses of the distance. This is the algorithm for a particular distance guess d. This is a much simpler version of the algorithm than in the paper, and I've left out a lot of the details that are necessary to make it work. The graph on the right is unweighted, and I'll be using it as an example. So the first step is to choose some nodes to be pivots and shortcutters. And how we choose those I'll talk about later, and what the roles of pivots and shortcutters will be in the next step. But for now, we're just going to choose some. And we're going to have that all pivots are shortcutters. So in the graph, the pivots are circled in red and are C and I, and the shortcutters are shown in green, and they are M, C, I, and H. So for each shortcutter, which again are the nodes that are circled in green, which are M, C, I, and H, we're going to define B to be the nodes that can reach the shortcutter within D hops, and F to be the nodes that are reachable from the shortcutter within D hops. Then we're going to add the edges from B to the shortcutter and from the shortcutter to F to the Hopset with weight equal to the distance from S. So in this example graph, the distance is 2. And so if we look at the node M, if we search backwards, we reach D. So we add that edge from D to M. And then if we search forward, we reach K and I. And I'm not showing the edge weights here, but the edge from M to I would have weight 2. And so these edges are getting added to the Hopset. So I'm showing them in the graph, but they're not actually going to be added to the graph that we're working on. Next, we search forwards and backwards to a limited distance D to partition the graph. We partition the graph such that nodes are in the same subgraph if they have the exact same relationship to each of the pivots. So in this example, again, the distance was 2, and so the nodes J, F, and H are in the same subgraph because they're both reachable from C at distance 2, and they're not reachable from the node I. And the node O is in a different subgraph because it was also reachable from I, and so it's in this overlap. And so in the picture, the different subgraphs are represented by the different colors. Now we remove nodes reached in both directions. So C reaches itself, I reaches itself, L and A, and so those 4 nodes are removed. And finally, we recurse on each group with a decreased distance. And I'll talk more about the decreasing distance later. For now, that's the whole algorithm for this distance guess, and then we would repeat the whole algorithm for each possible distance guess. So next I'll be getting into the analysis. Previously, Feynman in 2018 showed a simpler algorithm for reachability gets n to the 2/3 diameter. Jumbalapati, Liu, and Sidford in 2019 showed a similar algorithm to ours, but for reachability gets n to the 1/2 plus little of 1 diameter and runs in nearly linear time. Both of these algorithms are similar to ours. However, in the sequential version of Feynman 2018 and Jumbalapati, Liu, and Sidford 2019, they don't have distance limit searches, and the shortcutters and the pivots are the same nodes. In the Feynman 2018 paper, he uses a single pivot, and in the Jumbalapati, Liu, and Sidford paper, they use multi-pivots like ours. The previous papers and our analysis will look at just one path that we want to shortcut. So the path goes from S to T and is the shortest path between these 2 nodes. And we'll define ancestors to be nodes that can reach the path, which is this node that's circled in green. Analogously, descendants are nodes that can be reached by a node on the path. And bridges are nodes that can both reach a node on the path and can be reached by a node on the path. And so all nodes on the path itself are bridges. So in this example, the node that I've circled in green is a bridge, but really all of the nodes in this graph on the right are bridges. Both the Feynman 2018 paper and the Jumbalapati, Liu, and Sidford 2019 paper make progress in two ways. The first case is if the pivot is a bridge. In that case, the pivot will shortcut the path to 2 hops. So the vertex x, which is circled in green, searches forwards and reaches t, and adds a shortcut from x to t. It also searches backwards and reaches s, and so a shortcut is added from s to x. And now the path is just 2 hops, and it's basically done. The other case is that ancestors and descendants are pivots. In this case, the path is split into multiple subproblems. But they're able to show that the number of ancestors and descendants decreases significantly in the next level of recursion, making it more likely to get a bridge as a pivot. So the picture on the top right shows the graph with many ancestors and descendants, and the picture on the bottom right shows the next level of recursion. Now the path has been split up, but there are a lot less ancestors and descendants, and for some paths there aren't any at all. This means that it's much more likely to get a bridge at this level of recursion. For our analysis, the progress with the ancestors and descendants is the same. However, we care about distance, so the progress with bridges will be different, and that I'll talk about next. Here I'll talk about what happens to bridge nodes if they're selected as shortcutters or pivots in our algorithm. So in the first case, the pivot is on the path, and that's a very good case for us because we shortcut the path to 2 hops with exact distance. The second case is that the pivot is near the path, meaning that it shortcuts the path to 2 hops with a 1 plus epsilon distance approximation, and this is also a good case for us. The third case is that the bridge is far away from the path, and this is not a good case for us because it gives a bad approximation of the S to T path distance. So a near bridge would give a good approximation of the path, and that's what we want. So my goal is going to be to show that we actually only get near bridge pivots. Now let's look back at the algorithm. So the first step was to choose some nodes to be pivots and some to be shortcutters. So here I'll get to how we do that a little bit more specifically. First, we assign each node a level to become a pivot. So that means that at level of recursion R, all nodes where the level is equal to R are pivots. And then all nodes where the level minus L are at most R are shortcutters at level R. In other words, a node becomes a shortcutter at a particular level of recursion, and then it becomes a pivot L levels later. And also, this was the algorithm for a particular distance guess D. So in steps 2 and 3, the shortcutters and the pivots search to a limited distance of D. And finally, in step 4, the algorithm recurses on each subgroup with a decreased distance. So next I'll talk more about the limited distance search and why we decrease the search distance with each level of recursion. For the distance limited search, if we know the length of the path is d hops, then we want to search roughly d hops. So here we'll consider a shortest path from S to T, and we'll look at what happens when different bridge nodes are shortcutters. So in the first case, the shortcutter is on the path, which is shown in the graph, and the shortcutter is circled in green. Since the length of the path is d and the search distance is d, the shortcutter reaches the ends of the path in a search. So here the shortcutter would add the edge from S to the shortcutter and the edge from the shortcutter to T, and so the path would be shortcutted to 2 hops with exact distance. In the second case, the shortcutter is near the path. So again, in this case, the shortcutter will search and reach the ends of the path, and the path is shortcutted to 2 hops, but this time with a distance that's a 1 plus epsilon approximation. This means that if we get a near bridge, the search distance is long enough that we search to the ends of the path and we shortcut the path to 2 hops. The last case is that the shortcutter is a far bridge, and so some of the far bridges are going to be far enough away that with the distance limited search, they won't even reach the path. And so in this case, they won't affect the path. However, some of the far bridges are close enough that they can reach the path while still giving a bad approximation of the path. So these are a big problem for us because they don't give a good approximation and they can split the path into multiple subproblems without really making any progress when the shortcutter becomes a pivot. So shortly, I'll talk about why we don't get these bridges as pivots. So basically, if we know that the length of the path is d hops, then we want to search roughly d hops so that nearby bridges reach the ends of the paths in their searches, and very far away bridges don't reach the path at all, and then the problem still remains of these other far bridges. In each level of recursion, we're going to decrease the search distance to guess the new length of the path. So in the graph on top, we're searching to a distance of d. And in the graph on the bottom, I'm showing the next level of recursion, where now the path has been split into multiple recursive subproblems. And since we want to search roughly the length of the path, we decrease the search distance by a factor of k, so now the search distance is d over k, which is roughly the length of the subpaths. And k is a parameter of the algorithm that controls both the number of pivots and the search distance. And so here in this case, I'm showing an example where the path is split up pretty evenly, and so each subpath is roughly d over k. This doesn't always happen, and the general case is more difficult, but the idea is similar. So our goal was to show that there are no far bridge pivots, and here I'll be showing that. Here, we're going to consider a far bridge at some level of recursion r. The pivot is x and is circled in red. So at this point in the algorithm, the path has been split up into different subproblems, and the subproblem that we're looking at contains the subpath that goes from u to v. At this level of recursion, the search distance is d over k to the r. The distance from u to x and from x to v is at most d over k to the r. Otherwise, x would not reach the path when it searches, and therefore would not be a bridge pivot. Now we look at the pivot L level of recursion earlier. At this point in the algorithm, the path was longer, and the search distance and length of the path is d over k to the r minus L. Since x was a pivot at level r, we know that it's a shortcutter at level r minus L. This means that at this level, x searches for d over k to the r minus L forwards and backwards, and reaches the ends of the path. Now let's look at the distance of the path that goes from s to x to t, which is shown in red. This is the path that uses the shortcuts that the shortcutter x adds. The length of this path is at most the length of the s to t path, plus the distance from the path to x and from x to the path, which is the distance u to x and x to v. The length of the s to t path is d over k to the r minus L, and the distance from u to x and x to v is at most d over k to the r. Therefore, the length of the s to x to t path is at most d over k to the r minus L times 1 plus 2 over k to the L. We can set L such that k to the L over 2 equals 1 over epsilon, so that the distance of the path is 1 plus epsilon times the length of the s to t path. This means that at level r minus L, x was a near bridge, and so it would have shortcutted the path to 2 hops with a 1 plus epsilon approximation. I've just shown that we don't get any far bridge pivots, and this means that if we get a bridge pivot, then we must have gotten a near bridge, in which case the path is shortened to 2 hops with a good approximation of the distance. So here's the algorithm again, and 2 of the key features were that the shortcutters become pivots L levels of recursion later, and that we do a distance-limited search that decreases in each level of recursion. And this was the algorithm for a particular distance guess d, and so Once we've run the whole algorithm, we would repeat it for each possible guess of the distance. This again is a simplified version where a lot of the details that are necessary to make it work have been left out. In conclusion, I've showed the first algorithm for efficient construction of directed Hopsets, and in this talk I showed the sequential version for unweighted graphs, but we also handle the weighted case and give a parallel algorithm. And using the parallel algorithm, we can solve parallel approximate shortest paths.